Welcome back, everybody. Today, we're going to keep thinking about integration techniques and start in with a new technique. Last time we thought some more about the trig sub strategy and saw a number of different situations where it can be helpful to inject trig into our function and then look to use one of our Pythagorean theorem identities to collect things nicely so we can integrate. Today's technique, partial fractions, looks to take rational functions and break these up so we can integrate. And just as a quick reminder, a rational function, this is just a fraction where we have a polynomial up top and down below. And the idea behind what we're up to today comes from something that we're familiar with. So for example, down here, we have a sum of two fractions. If we would like to combine these and write these as a single fraction, well, what we'd like to do then is get a common denominator. And so here that common denominator is going to have to be x plus 3 times x minus 1. And so if we multiply our second fraction, top and bottom by what it needs, and our right-hand side fraction, top and bottom by what it needs, we end up with what's here in the middle. And if we felt so inclined, we could do a little simplification up here in the top. And when the dust settles, we'll be left with this fraction over here. And so the idea behind partial fractions is we like to actually undo this process. We'd like to move back to what we had to start with. The reason being, if we look at what is over here on the right, well, thinking about integrating, well, this thing on the right is not so clear how we are to find an antiderivative here. But over on the left, written as a sum of these kind of simpler pieces, this is something that we can actually integrate just piece by piece. And so this is really the idea behind partial fractions, taking a rational function and breaking it up as simpler pieces so that we can then integrate. Right, that, in a nutshell, is what partial fractions does. Let's start in and talk about how partial fractions actually works. Okay, so if we have a rational function here, some n of x over d of x, so n for numerator, d for denominator, right? Both of these are polynomials. With the degree of our top polynomial less than the degree of our denominator polynomial. And we've gone ahead and factored our denominator as much as possible. Then what partial fractions does is it associates to each factor or pile of factors, we'll see what I mean by that in a minute, gets an associated term. And so over here, the idea is we start with our original rational function. Well, for each factor or pile of factors in our denominator polynomial, we'll get a particular term on the right-hand side. And partial fraction says that our original function is going to be the sum of these simpler pieces. The catch is that these simpler pieces come with some unknowns to start, some parameters that we don't know. And so once we kind of write down the associated terms, we then need to actually find what these are so that we have a completely described equation here. Again, for us, the payoff in working out partial fractions here is that we can now, by looking at these simpler pieces, look to integrate what we have. All right. So that's the basic flavor of how partial fractions works. Let's look at a halfways specific, halfways general example of a partial fraction decomposition, where over here on the left we have sort of the rational function that we're starting with. Then over here on the right are all the different terms that partial fraction says gets associated to our factors. The reason I've kind of done it halfways like this, halfways general, halfways specific, is that the true general formulas for what we're talking about are kind of horrible to look at. And so I think that this kind of halfways example will give us a clearer idea of what to do and what partial fractions says gets associated to each kind of factor. Okay, so to start off, we have some rational function here on the left. We have some denominator and a numerator polynomial, which I haven't specified because it doesn't really matter what this is. All that matters is that this polynomial's degree is less than the degree of our denominator. And here, because we have our denominator all specified, we can actually figure out what that would have to be. Here we have a linear factor, so that'll give us a 1x, and then here we have a linear factor cubed, so that'll give us an x cubed if we imagine, distributing this all out. And so let me just maybe for the moment write kind of the powers of x that each of these will give us the highest powers of x. So we'll have x from the first one, x cubed times the second. Our quadratic term here gives us an x squared. And then on the right, we have x squared, but we have this term squared. And so at the end of the day, all right, this will be x squared, which would be x to the fourth. If we imagine distributing that all out. Right? And so here, if we multiply these together, the exponents will add, and we'll get 1 plus 3 plus 2 plus 4. And so altogether, that gives us a degree of 10. Right? So if we went through the trouble of distributing this whole denominator polynomial out, the highest power of x that we'd see is x to the 10th. And so for us to start in with partial fractions, we need our polynomial up top to have a degree less than that. It could be degree 9, degree 8, degree 7. It could even be all the way down to just a constant polynomial. As long as its degree is less than 10, then we're good to go. And partial fraction says, well, to each one of these factors, or piles of factors, and so here I'm using the pile of factor language to mean we have some factor with an exponent. We're going to get an associated term over here on the right, or in some cases, a handful of terms. All right, so here's how this goes. If we just have a linear factor here, like x minus 3, partial fraction says we get one term, and we're going to have that x minus 3 in the bottom, but we could have possibly some constant up top that we don't know. So we'll just label that as a. Now, if our linear factor is a pile of linear factors, so it has an exponent here, then we're actually going to get a number of terms equal to that exponent. So we'll have 1, 2, 3 terms associated to that pile, where the exponent on the denominator goes up from 1 up to the exponent that we see from our function. Right? And in the numerator, because x plus 1 here is linear, right? Just degree 1. Then in the numerator here, we only have to allow for the possibility of there being some constants up there that we'll need to find. Next, we have a quadratic over here. And in general, if we do have a quadratic, right, we like to factor it as much as possible. But I claim that this quadratic is actually irreducible. In other words, no matter how hard we try, we can't factor this thing. And a couple ways we could see that. If we went through the trouble of using the quadratic formula, we'd see that there's no real roots to our quadratic polynomial there. Or if we wanted to think more visually, if we were to graph this thing, the fact that it has no real roots just means that it doesn't cross the x-axis. So it's either going to be up here, up top, or down below. So something like that. And here, if we actually jump over to Desmos, we can see this in action. Here's our denominator there, and we can see, this parabola is never going to cross the x-axis, and so this thing's not going to factor. And so partial fraction says that associated to a irreducible quadratic like this, we're going to have one term. But because it's a quadratic, because the degree of this polynomial, this factor, is 2, we have to actually allow for the possibility of a linear polynomial up top. So we don't just have, say, a letter. We have something times x plus something else. Lastly, if we have an irreducible quadratic to a power, right, we have a pile of these irreducible quadratics, then we're going to get, again, the number of factors associated to it equal to that exponent. And just real quick, so x squared plus 5, we can see very quickly that this is going to be irreducible. Right? If it was just x squared, it'd be our favorite parabola through the origin. Plus 5 is going to push that straight up by 5 units, and so this is not going to cross the x-axis anywhere, and so this cannot factor over the real numbers. All right, and so partial fraction says, hey, to this pile of irreducible quadratic factors, we're going to get 2 terms. Again, 2 terms coming from the fact that the exponent was 2. And again, since our denominator had an irreducible quadratic, in the numerator, we have to allow for a degree 1 polynomial in each of these cases. And so over here on the right is what partial fraction says our rational function is going to break up into, right, these simpler pieces. And at this point, right, if we wanted to figure out exactly what these pieces are, we just have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 unknowns to figure out. And that would take a whole lot of work. And in general, it does take some work to find these, but it won't be this bad for us. Right? This is a big example meant to show us these different possibilities. Okay. Let's dive in now and look at a specific example where we're integrating, and we'll put this strategy to work. Okay. So here, we're looking to compute this integral here of this rational function. Right? We have a polynomial up top, a polynomial in the bottom. All right, indeed, this is a rational function. And partial fractions isn't always necessary if we have a rational function, right? We could have something where maybe if the derivative of this denominator polynomial was, floating around up top, maybe this would just be a u sub, or something like that. Maybe if we just had an x cubed or something in the bottom, right? Then we could just algebraically mess with this, break up this as a bunch of fractions with x cubed in the denominator and see what this worked out to be. But we do have the second term in the bottom. And so the partial fractions thought is, hey, maybe we could take this rational function and break it up in terms of simpler pieces and then try and integrate. And so the thing we have to check is if the degree of the top is less than the degree of the bottom, and up top the degree is 2, the bottom degree is 3, and so we are good to go. And what we'd like to do now is take our denominator and factor it as much as possible so that we can then see what sorts of terms get associated to our function on the right-hand side of our partial fractions equation. And our denominator here has a nice common factor of x squared in each of the two terms. We can pull that out, and what's left is an x on the left and a 2 on the right. And that's all we can do there. And so now, if we take our rational function, with its denominator all factored, partial fractions tells us what to associate to each one of these factors or pile of factors. Right? To this x squared, right, we have a linear polynomial x squared, so we have a pile of x's, right? And because of the exponent of 2, we're going to get associated 2 terms, right, where the exponent on that factor leads up to the exponent that we see, right, starting at 1 and ending at 2 in our case. Right, and because x is linear, we'll just have a unknown constant up top. And then we also have this factor x plus 2, that's linear. And so partial fraction says we'll associate 1 term for it, and the numerator could just be some constant. So here's how partial fraction says our rational function will break up. Our job now is to just go ahead and find these unknowns. We need to figure out what a, b, and c are so that this entire right-hand side of the equation is known. And so if we want to do that, the first step is to clear denominators. Right? No one likes thinking about fractions if we don't want to, and so let's actually start just by getting rid of these. And what's nice is that since these denominators from our decomposition, all come from the factors of our denominator here on the left, we can always clear denominators just by multiplying by our original denominator. And so what I am saying here is, well, let's take both sides here, left and the right, and multiply by x squared times x plus 2. Over on the left as well, we'll get x squared times x plus 2, right, times this. All right, and let's just see what happens as we do some algebra. Right, on the left, our denominators are just going to cancel out. Now on the right, this factor we're multiplying by is going to distribute to each one of these 3 terms. And in each one, something different is going to cancel. in this a over x term, let me write it in here so we can see it. All right, so we'll get a x squared times x plus 2. And here, just one of these x's is going to cancel off with the x in the bottom. We'll be left with x times x plus 2. When we distribute to the second term, both of the x's will cancel off. And we'll just be left with the x plus 2. And on the right, the x plus 2 is what's going to go. And we'll just be left with the x squared. And so what we're left with is this nice polynomial equation now. No more fractions to worry about. And what's useful to us is that this equation holds for any and every x and what that means for us is that we can plug in any x that we'd like and we'll get a true equation, right? And notice what would happen if we plugged in an x wherever we saw an x. What we'd be left with are numbers and our unknowns, a, b, and c. And so what we'd like to do is plug in really whatever x we'd like to get some equations relating our unknowns and then use these equations to find out what these are. Now, while we can technically plug in any x we feel like, we could plug in x equals 1005 if we wanted. There can be some nice x's that will end up kind of clearing out and killing off a number of the terms and make our life easier. And so here, looking at our equation, are there any x's that you think would be nice and clean to plug in? So take the x's that you thought of and plug those in. See what happens and see if you can, by plugging in x's, get enough information to find a, b, and c. And if you can do that, go ahead and see if you can then integrate the function that we're left with in its simpler pieces. Pause the video and see how far you can get. All right, so the x's that stand out to me come from these linear factors over on the right. And right away, what stands out to me is that x equals 0 for 1. That's going to kill off this first term and this third term. That would be nice. And also, if we wanted to zero out these factors of x plus 2, well, plugging in -2 would make that happen. And so those stand out to me as two nice x's to think about. We might need to do some random plugging in after that, but let's at least start with those. Oh, let me try and leave our original equation on the screen. So if we plug in x equals 0, we're going to get 0 plus 0 minus 2 on the left. And this first term will become 0 because we have a, whatever that is, times 0 times 2. So that'll be a big 0 plus b times 0 plus 2 plus 0. And actually, in this case, everything except our b disappears, and we can just quickly solve for b and find what that is. So that's nice. All right, so 1 down, we know b, we just have 2 to go. Let's see what happens if we plug in -2. If we plug in -2 for x, then we'll get, so +4 for x squared, and -2 for this x, and this first and second term will go away, and we'll be left with c times +4. And in this case, again, all of our unknowns except for one disappear, and we can quickly solve for what c is. All right. Next, we don't have any more like real natural x's to think about plugging in, and so we just need to plug in something else. Hopefully something that's not too challenging, just to make our life easy. I used x equals 1, and so we had plugging in for x squared and x, we get 5 plus 3 minus 2 on the left. And then a times 1 times, this was, let me just record where these are coming from here, right? This was a x, and then this was x plus 2, and this was an x plus 2 there, and then we had also c x squared. And so plugging in 1 for our x's gives us this equation. All right, it involves a, b, and c, but right, we already know b and c, and so we can actually plug those in. All right, so b is minus 1, and c is 3. And so plugging those in, we have an equation just involving some numbers in a, and we can solve that for a. And with that, we know all three of our unknowns, and so we know through partial fractions exactly how our function decomposes, breaks apart. And so here, I've just taken our original, partial fractions equation here and just filled in our a, b, and c from what we found them to be. All right, and so since this is how our rational function breaks up, well, the integral of our rational function is the integral of these pieces over here on the right. And I claim that now we are all set to integrate each one of these. Right? On the left, if we want, we could think of this, pull out that numerator of 2. We just need to integrate 1 over x. Right? That's natural log of absolute value of x. Over on the right here in the middle, this is just a power of x, right? So this is what? Minus x to the minus 2. And so we could integrate that, add 1 to the exponent, divide. Over here on the right, this might look a little bit strange, and I claim that if we kind of do a similar trick to over on the first one, kind of pull out the 3, because this is a linear denominator, I claim that this is also going to be a natural log antiderivative. And so let's just write it down, what we get, and then say a few words. All right, so here we go. As we take our antiderivatives, I claim that antiderivative over here on the right is just the natural log of absolute value of x plus 2, right, times that constant multiple of 3. And so right there, those are the antiderivatives to our original rational function, right, that we were able to work out by breaking this apart using partial fractions. All right. Now I want to say just a couple words about our last antiderivative here, because there's something that we need to be careful of. And so here, the reason that this is the antiderivative really is that if we do a u sub, if we work that out, letting u be our whole denominator, the x plus 2, well then, if we take the differential here, well, the derivative of x is just 1. And so our differential equation here is that du is actually just dx. And so through this substitution, the integral becomes literally, right, 1 over u. And that's a function we know antiderivatives for. It's natural log absolute value of u. Right, and then plugging back in for u, we get what we saw up here. Right, and I have this 1 over u starred because this is really why we get antiderivative involving natural log. We want to be careful that we don't think that any time we have, say, something in the denominator that we get a natural log antiderivative. Right, if we have 1 over cosine, that antiderivative is not natural log of cosine. Right? We could just take the derivative of this thing on the right and see that we're not going to get 1 over cosine. Similarly, if we had 1 over this cubic polynomial, the antiderivatives are not going to be natural log of the denominator, essentially because, right, if we took the derivative of this thing, we'd get 1 over that cubic polynomial times the derivative, right? In this case, 3x squared plus 7, which we do not see up in the top, right? And that's really the kicker here, right? For these functions on the left, we're missing the derivatives of the denominator up top. And so the antiderivative won't involve natural log here. We'd have to go some other direction. And so the point I want to make through all of this is that while we'll be able to, just through getting more comfortable with these computations, take something like 3 over x plus 2 and just say, okay, the antiderivative is going to be 3 times natural log of x plus 2. We want to keep in mind why that is. And the reason why is because, well, if we did a u sub, it would get us literally to this form, 1 over u, right? And that antiderivative is natural log of absolute value of u. All right, good work today, everybody. If you have any questions, post those to Piazza, and I'll see you next time.